Consider a solid object shaped like this. Okay? And assume you are applying equal and opposite forces at the ends of this object like this. So basically, you are trying to stretch the object. Fine. Now tell me, as the magnitude of the force increases, at which point is the object most likely to break? Type your answers in chat, or okay, you can unmute and tell.
Sir, the midpoint, somewhere near the midpoint.
Okay. Others, Yusuf, Aishwarya, what do you think? Where is it likely to break as we go on increasing the force with which we are trying to stretch this object?
So at the midpoint.
Okay. So basically, wherever it is narrowest, you feel it is going to break there. And that's correct only. That is where it is going to break. But can any of you justify this uh, in like mathematically or by writing equations? Can you justify this? Like what is different? Fine, I don't need complete equations and all also. As we apply this outward force at both ends, what is different from this cross section to any other cross section? Why does it break only there?
Sir, the area.
Okay, the area there is less. So,
The force that is applied gets spread over the course of the cross section and then
what did you say? The force which is applied?
it gets distributed across the cross section.
Okay,
And since this at the midpoint, the cross section is the smallest, it's easier to break due to the pressure which is being applied.
okay. Fine. You use the term pressure. Okay, fine. See, we are applying equal force at both the ends, right? Therefore, the net force on this solid object is zero. If net force is zero on the entire object, then on small parts of the object also the net force will be zero. Now you consider any random cross section. Let's consider that orange one. Look at the forces that act on the part of the object which is to its left. Okay, if you consider that orange cross section, now you are trying to stretch the object by applying forces to the, by applying outward forces like this. So there will be a tension developed in it. So on that orange cross section, there will be a tension acting this way. And the entire solid object is in equilibrium, means this part will also be in equilibrium. That means tension will be equal to the force you applied, F. So basically what it means is you are generating the same tension equal to F everywhere in this object. On every cross section of this object, the tension generated is the same. But at different points, the area of cross section is different. Okay. So if the force, the tension is same everywhere, but area of cross section is different, means the stress will be non-uniform. Okay. Tension is uniform, but the stress is non-uniform. And how do you calculate stress? Perpendicular force per unit area of cross section. The perpendicular force tension is same for all these cross sections, but at the midpoint, the cross sectional area is the least, minimum. If cross sectional area is minimum, then tension per unit area, the stress, longitudinal stress to be specific, will be maximum at this point for any amount of force you apply. Therefore, as you increase this force applied, stress increases everywhere, but here the stress will be the highest. Okay. So at that point or at that cross section, the stress will first become equal to the breaking stress of this material. Okay. At other points also stress is being created, but it's not as high as this point. Fine. Suppose the breaking stress of this material is some, let's say 200 Newton per meter square. Okay, let's say that is the breaking stress. Now, if you apply a small amount of force, let's say you generate a stress of 50 Newton per meter square here, maybe 25 here and 20 here. Tension is same everywhere, but areas of cross section are different, so the stresses will be different. So you may generate stresses like this. Increase the force. If you increase the force, then maybe you generate stresses like 100 Newton per meter square here, 50 here, and 40 here. Okay, so stress is increasing everywhere, but still stress at this cross section is the highest. Okay, as you go on increasing this force from 100 at one instant, at one value of the applied force, this will touch 200, this will become 80, this will become 100. So 80, 100 are not enough to break this object, but 200 is enough to break the object because that material's breaking stress is only 200 Newton per meter square. That is why it will break there. Okay, so remember, to break an object or to damage an object, there is a certain amount of stress that you need to produce. Okay, that's called breaking stress. Wherever that gets produced, the object breaks. Okay. Let's solve one problem based on this. Suppose there's a wire of cross-sectional area, some 4 centimeters square. Okay, quite reasonable, thick wire, 2 centimeter by 2 centimeter, 4 centimeter square. And let's say that wire connects to blocks. Okay, just a moment, I'll draw the system. Okay, so the cross-sectional area of the wire connecting the two blocks is 4 centimeter square. It's a very light wire. I mean, its mass is negligible. Okay, now what is my, or what do I want to convey by saying that mass is negligible? In a light inextensible string, okay, the tension will be same everywhere. So if the mass of a string is negligible, you can assume the tension is uniform. If the string has mass, then tension will vary from point to point. So here you assume tension in that string is uniform if it is generated. So the wire's cross-sectional area is 4 centimeters square, and the breaking stress of the material with which it is made, let's say, okay, I just have to give you some random value. Let's say it is 100 Newton per meter square. So once that much stress is generated, it is going to break. Fine. Now, assume this system is pulled to the right by applying a force, horizontal force F. F is unknown. Now you apply a small force, the system will slide with a small acceleration. There will be a small amount of tension generated in that string. It may not be enough to break the string. But if you apply sufficient amount of force, you can generate sufficient tension in the string, which can break the string. Okay? So the question is to find out the maximum force that you can apply without breaking the string. So if you're asked a question like this, basically the first thing that you need to do is think of how this force is related to the breaking of this string. Okay, and that I kind of already told you, that force generates tension in the string. Okay, so how you proceed here is assume some force F. Okay, don't take any numerical value, let it be F itself. In terms of F, derive tension in this string. And from tension, you write expression for stress. So you will be writing stress in terms of the force F. And then you know what is the limit of the stress. So you will get the limit of the force. Okay, that is how you are supposed to solve. Do this, all of you. I'll give you 3 minutes. Solve carefully. So first step is to express T in terms of F. Next step is to express longitudinal stress in the string in terms of F. And the third step is to just write that longitudinal stress should be less than or equal to 100 Newton per meter square. From there, you'll automatically get the maximum value of F. Okay. Do this. Okay, can one of you tell me how you will express tension in terms of the force? Okay, we had solved questions like this in laws of motion. Anyway, the 3 kg and 2 kg are connected by this string. The string is already taut. Okay, so basically, what will happen when you apply a force, the 3 kg, 2 kg will move together with a common acceleration. Now, why am I talking about acceleration? Our aim is to derive tension. Tension is a force. If you want to calculate a force, you need to know the acceleration of the object on which the force is acting. Fine. So, visualize the motion of the entire system first. 3 kg, 2 kg together move with a common acceleration. Now, for the entire system, F is giving that acceleration. So, you can write F is equal to whatever be the force F. F is equal to total mass of the system multiplied with the common acceleration. So, you can say acceleration is F by 5. If F is in SI units, we'll consider everything in SI units. Once you know acceleration, how to calculate tension? Can any of you tell me? If you know the acceleration of these blocks, how will you calculate tension from it? Generally, if you know acceleration, how do you calculate force? How are force and acceleration related? Rishi,
F is equal to ma, sir.
F net is equal to ma. Okay. Now, our aim is to derive tension. Now, tension acts on both the blocks. It acts on one block to the right and one block to the left. So, if you write F net equal to ma for the whole system, tension won't appear in that equation because there are two tensions, they'll cancel. So you will need to write F net equal to ma for only one of these blocks. Then tension will appear in that equation. So consider the 3 kg block or 2 kg. You can take any one of them. I'll prefer taking the 3 kg because on 3 kg, the net force itself is tension. If you write the equation for 2 kg, no, there is a force F acting to the right and tension acting to the left. I'll have to write F minus T. For 3 kg, I can directly write only T. Okay? So that way it is easier. So writing F net equal to ma for the 3 kg block, you get tension is equal to mass into acceleration. Acceleration we found out as F by 5. That's all. Therefore, whatever be the force F, tension will be 3F by 5. First part done. Then the second part. Now you know the tension in the string. Divide by its area of cross section, you will get the stress in the string. Therefore, longitudinal stress. The string is given to be of negligible mass. So the tension will be same everywhere in the string. That means the stress also will be same everywhere in the string. The longitudinal stress will be tension by cross-sectional area. Tension is 3F by 5 divided by area of cross-section is given 4 centimeter square. That becomes 4 into 10 power minus 4 meter square. Okay, you should be very comfortable converting units also. Centimeter square is 10 power minus 2 meter whole square. Becomes 10 power minus 4 meter square. Therefore, the longitudinal stress in the string, depending on the force F, becomes 3 by 5 into 4 is 20. 10 power minus 4 goes to the numerator, 10 power 4 multiplied with F. And this stress should not exceed 100. So this should be less than or equal to 100. That's all. From there, you get the maximum force that you can apply. 20, 10 power 4 becomes 10 power 3. 10, 100 and 10 power 3 will just be a 10. So F should be less than or equal to 2 by 30. Means less than or equal to 1 by 15 newtons. A very small amount of force. Okay, any force greater than this will generate enough tension in the string to break the string. Simple. Is this clear to all of you? Any doubts in this? Okay. The same question can be modified also. You can be given pulley block systems and be asked what maximum mass can be connected such that the string does not break. Okay, let's try one problem like that also. Why not? Just a moment, I'll draw a diagram. Consider a simple Atwood machine like this. Okay, assume it is ideal, means the pulley is frictionless, the string is light and inextensible. We have dealt with situations like this. Now, the string that connects the blocks, assume its cross-sectional area is 2 centimeters square. Okay, and its breaking stress, let it be some 10 power 5 Newton per meter square. Okay, that is the breaking stress. Now, suppose this right side mass was, or okay, the problem is, or the question is to calculate maximum mass M such that the string does not break. Okay. So when you are given a question like this, you should first think, why should there be a limit to that mass? Okay. Imagine that mass was not even present. What will happen? Can any of you describe what happens if that other mass is not present?
So the thread with the mass will just fall off towards the left side.
The 2 kg will just fall off. Will there be any tension generated in the thread?
No, sir.
No, the string is massless and there's no mass connected on the other side. 2 kg will fall under the influence of gravity and the thread will just go along with it. Okay, so in that case, tension is zero, stress is zero. There's no reason for it to break. But when you add some mass on this side, okay, 2 kg's weight will try to make the system go down on this side. Okay, or it will try to make the system move in one way. M's weight will try to make the system move in another way. Then tension will get generated. Okay, because both blocks ultimately have to move in one direction only. I mean, one sense only. So which sense they follow depends on which is heavier. You know that. Okay. So now tension will get generated in the block. And greater the mass you connect here, greater the tension that gets generated in the string. Okay. I think I said block. Tension gets generated in the string. So there will be a limit to the mass that you can connect here because there is a limit to the stress which the string can bear. Okay. Now Newton's laws don't include stress. They'll be written in terms of forces. And based on force, you can calculate stress. So here also, how you approach the problem is assume some mass M is connected, unknown mass. Based on the mass M and 2 kg, derive an expression for tension generated in this rope. Obviously, that tension will be in terms of the mass M. Like in the previous problem, tension was in terms of F. Here, tension will be in terms of M. If you can get an expression for tension in terms of M, dividing it by area of cross section will give you stress in terms of M. And you know the limit for stress. From there, you will get the limit for the mass M. Okay. Do this, all of you. I'll give you 3 minutes. Just a moment. So in order to derive tension in terms of M first, let's assume M accelerates upward and 2 kg accelerates downwards. See, the assumption may be wrong also. In that case, A will come out negative. Tension answer will come out correct anyway. Okay, the equations will take care of that. Okay, Aishwarya, tell me what equation you wrote for 2 kg and what equation you wrote for M.
So 20 minus t is equal to 2m.
Okay, good. For the block, other block
10 minus 10m, t minus 10m is equal to mm.
is equal to MA. Okay. Our aim is to get tension in terms of M here. So we should not eliminate T, we should eliminate A. So what we'll do is we'll take A from the first equation and put it in the second equation. From the first equation, A becomes 20 minus T whole divided by 2. Substitute it here. You get T minus 10M is equal to M into 20 minus T divided by 2. Okay. We'll have to readjust this equation. So 2T minus 10M, okay, minus 20M is equal to 20M minus M into T. send it that side. So 2 plus m into T is equal to 20m, 20m becomes 40m. Okay, we got some expression for tension in terms of mass. T is equal to 40m divided by 2 plus m. Is this the same that you got?
Sir, yes, sir.
Okay. Next, tension divided by the area of cross section gives us the stress. Area of cross section is given 2 centimeters square. Therefore, longitudinal stress becomes tension divided by cross sectional area 40m divided by 2 plus m, that is tension, divided by the area of cross section. Area of cross section is 2 centimeters square. That becomes 2 into 10 power minus 4 meters square. And this longitudinal stress should be less than or equal to the breaking stress. That is given as 10 power 5. Okay. 10 power minus 4 goes to numerator, becomes 10 power 4. 10 power 4, 10 power 5, 110 remains on that side. This 10 and this 10 you cancel. So you get 4 is equal to 2 plus m into 2. Eh? How did this happen? So you get 4 is equal to 4 plus 2m. That means m is 0. Is there some mistake here? Just a moment, let me check. Okay, maybe the assumption was wrong, that acceleration is in the upward direction. Just a moment. Twenty minus t is 2a, and on that side t minus m into 10, we took acceleration due to gravity as 10, is equal to mass into acceleration, correct? So you get acceleration as 20 minus t divided by 2 whole divided by 2. Put it here. Okay, so 2t minus 20m is equal to 20m minus mt. So 2 plus m into t is equal to 40m. 40m by 2 plus m divided by area of cross section should be less than or equal to the breaking stress. This way we are getting m as 0, but m0 won't break the string. Okay, we'll see what is wrong with this approach. How did you get 2 from this? Okay, let's check. Let's assume acceleration the other way and see if we get any different equations. Assume m accelerates in the downward direction. 2 kg accelerates upwards. Then the equation you write for 2 kg will be t minus 20 is equal to 2a. And the equation you write for m will be mg, that is 10m, minus t is equal to ma. Okay. Getting a from the first equation, you get t minus 20 whole divided by 2. Substituting in the second equation, t minus 20 whole divided by 2. Cross multiplying, 20m minus 2t is equal to mt minus 20m. We are getting the same equation. 40m is equal to 2 plus m into t. Earlier also we got the same thing. Divide by area of cross section. So 2 into 10 power minus 4. That's the stress, and this should be less than or equal to breaking stress of 10 power 5.
So can you show the calculation part of the first time you did it?
We got the same equation the first time also.
Sir, I think you made a calculation mistake. 4 plus 2m, and so m should be 2 only, right? A little bit down.
Where?
Yeah, because or here 4.
Here.
Yeah, so it becomes 4.
No, there is a 2 also, no?
Oh, yeah. Yes, sir. My bad.
Okay, if we solve it this way, we are getting m as 0. Let's see. What does that suggest? See, basically, if m is 0, tension will be 0, it won't break. Maybe the answer is suggesting that this string will never break. No, that is not possible. It has to. Okay, wait. That is possible. It may never break also. Okay. Why? Listen. If m is very light, okay, if the mass m is tending to 0, 2 kg will almost be under free fall. Tension will tend to 0. Suppose m becomes very heavy. Okay, then the system will start accelerating in the opposite direction. If m is heavier than 2 kg, system will start accelerating in the opposite. Let's assume m is 2 kg first. Okay. If this mass is also 2 kg, acceleration is 0. Both sides balance will be there. Acceleration is 0. Means tension will be 20 and both sides tension will balance the weights. Tension 20 Newton. Tension 20 Newton generates a stress of how much? 20 divided by area of cross section is 2 into 10 power minus 4. So that becomes 10 power. Okay. Okay. If m is exactly 2 kg, the longitudinal stress is becoming 10 power 5. Okay, what if m is more than 2 kg? Or why did we not get that answer of 2 kg? Let's check just a moment. Correct, correct. There's a silly mistake here. There is an m that I forgot to include. So 4m is equal to 2 plus m multiplied with 2. Okay, right. So 4m becomes 2m plus 2 into 2 is 4. Okay, now send 2m this side. You get 2m is equal to 4. That means m is equal to 2 kg. Correct. Correct. The equation should give the correct answer anyway. Mistake from my side. Fine. Good that you pointed it out. Even when you solve it the other way, again, that m if you consider, then you will get the answer. So the maximum mass that you can place on the other side is 2 kg. Okay, for 2 kg, it may just be able to withstand. Anything greater than that, it will break. Okay. So questions like this are quite common based on breaking stress. They'll give you one situation, they'll ask you breaking stress, or they can give you breaking stress in one situation and ask you in another situation and so on. I'll give you some problems like that in the next worksheet. So till now, what we discussed was mostly about longitudinal stress, perpendicular force acting per unit area. Okay, longitudinal stress produces longitudinal strain. It will either elongate the object or compress the object. Another kind of stress, okay, is tangential stress, something that you see in the second and third pictures of this, second and third parts of this diagram. Okay, where you apply a force parallel to a surface, parallel to an area of cross section. Okay, let me use these diagrams itself. Just a moment. Right. So imagine applying a force F tangential to that upper surface of a cylinder. Okay. You should ensure that the lower surface is not moving. Now, how do you ensure that the lower surface is not moving? By applying another force here also, such that the net force on this system is 0. Okay. Or you can also assume that it is rigidly connected to the ground. If it is fixed to a rigid surface, then that lower surface won't move anyway. You apply a stress, a tangential stress like this, means you apply a force parallel to the area of cross section. Then, see, in some cases, you may be able to notice it. Like in case of a book, you apply a tangential force on the upper cover of the book. Definitely, you will see the book deforming. Okay. Uh, in a more rigid object, something like a steel cylinder, okay, you apply a tangential force, you may not actually notice the cylinder getting deformed like this, but at the molecular level, a little bit of disturbance will definitely happen. No object in real life is 100% rigid. When you apply a stress, a little bit of deformation will definitely happen. Even whether it is steel or any metal or even diamond, some deformation will be there. In most cases, it will be negligible. You won't be able to notice it, but it will happen. Okay. Now, the kind of stress we are creating here or applying here is called tangential stress. It's also called as shear stress. Basically, what is shear? Uh, any object, if you think of it as layers, okay, book is a very good example actually. Book is made up of many layers, which are basically papers, right? When you apply a stress in such a way that the layers slide over each other, okay, the layers sliding over each other is what you call as shear. Fine. So if you apply a stress which does that, that kind of stress is called tangential stress or shear stress. So how do you make that happen? By applying a force parallel to the area of cross section. So parallel force per unit area of cross section is how you calculate tangential stress. The SI unit and all will be the same. Any kind of stress has the same unit Newton per meter square. Sometimes they may give you the stress in terms of pascals. Pascal, Newton per meter square are the same. Okay. As a result of tangential stress, observe carefully what happens. You consider two layers of this cylinder. The bottommost layer, which I am shading in yellow, and the topmost layer, okay, which I will shade in. Wait, the bottommost layer I have shaded in orange. Okay, let's avoid confusion. The bottommost layer, I'll shade it in black. Topmost layer of that cylinder, I'll shade it in orange. Now we are forcefully not allowing the bottom layer to move. So it stays there itself. The black one stays there itself. The topmost layer, the one which is shaded in orange, undergoes some displacement relative to the bottommost layer. Okay, that displacement is delta x. So how would you define delta x? It's the relative displacement between two layers of the object. Compared to one layer, how much extra displacement the other layer undergoes. Okay. See, we took the bottommost layer as the reference. With respect to bottommost, the topmost slides by delta x. You can take any other layer also as reference. For example, I can consider this one layer here shaded in green. Now that layer undergoes a little bit of displacement because it's not rigidly attached to anything. There is a small displacement that it undergoes. But the topmost layer undergoes more deformation or more displacement. I should not say deformation, more displacement than this. Okay. So suppose the green layer undergoes a displacement of delta x1 and the topmost layer undergoes a displacement of delta x2. Then what is their relative displacement? Delta x2 minus delta x1. Okay, that you will have to consider. Or you can visualize it like this. Let me show you a better diagram. Just the side view if you consider. Okay. After deformation, assume this is the situation. So the bottommost layer was shaded in black. It stays where it is, where it was. One layer in between was shaded in green. And the topmost layer was shaded in orange. Okay. All these layers were initially here. Okay. The edges of all these layers were initially here. Let's draw one more reference line over here and one here. Okay. So this is the displacement of the orange layer. I'll call it as S1. This is the absolute displacement, actual displacement. This is the displacement of the green layer. I'll call it S2. And for the black one, it is 0. S3 is 0. It could be non-zero also, let it be, but in this case, it is 0. Fine. Now, when the object deforms like this, there is a certain angle made by this surface now. Let's call it theta. And okay. the distance from the bottommost layer to the topmost layer. Let's call it y1. The distance from bottommost layer to this middle layer, let's call it y2. Fine. Okay. So when you apply a force tangential to an area of cross section, you see this kind of deformation happening. So this is the force parallel to that surface. Force per unit area, that parallel force per unit area will give you the tangential stress. Now, corresponding to every kind of stress, there is a kind of strain, there's a kind of deformation, right? In this case, the object is neither getting elongated nor compressed. Its shape is changing. Okay. So this kind of deformation is called shear strain. You apply shear stress, what you produce is shear strain. And how is it measured? Okay. The formula is for shear strain, relative displacement between layers divided by the distance between the layers. Okay, what do I mean by that? Now you take the topmost and bottommost layers, orange and black one. Black one hasn't displaced at all, but the orange one has undergone a displacement of S1. So what is the relative displacement between them? S1, which in the diagram given in your book is delta x. Okay, I'll remove these delta x2 and all to avoid confusion. This delta x itself is the displacement S1. Okay. Divided by relative displacement between layers divided by distance between the two layers. What's the distance from the black layer to the orange layer? Y1. In this diagram, in the diagram given in your book, it will be this length L. Okay. Therefore, shear strain is measured as delta x, relative displacement between two layers, divided by the distance between the two layers, L. You can call it as y also, the y coordinate. Okay. Now see, if it's a solid object, no, this deformation will be very small. It will happen, but it will be a very small deformation. So the angle theta that you see here is going to be a small angle. Okay. Now in that diagram itself, you can see that tan theta is opposite. Opposite is what? Delta x divided by adjacent is what? L. And delta x by L itself is the shear strain. No, by definition, it is like that. So the angle by which the body deforms itself is the shear strain, tan of the angle. And because the angle is small, okay, because angle is small, tan theta is approximately equal to theta itself. We had discussed this many times. For small angles, if the angle is taken in radians, for small angles, tan theta, sin theta, both will be equal to theta itself. Cos theta will be equal to 1. Sin theta, tan theta will be equal to theta itself. Therefore, shear strain can be calculated as relative displacement divided by the distance between the layers, which also becomes angle by which the body deforms. And that angle must be in radians. Because only in radians you can approximate sin theta to theta when theta is a small angle. Okay. Now, why did I consider that middle layer? You can see in this diagram itself that this angle theta is same as this angle theta. To calculate that angle theta, there are two ways. There are multiple ways. What are the multiple ways? You can take any pair of layers. That is what I wanted to show you. If you take the orange layer and the black layer, their relative displacement is S1, the distance between them is Y1. That ratio will be equal to theta itself. Okay. Suppose you take the orange layer and the green layer. Now, orange layer has undergone displacement S1, green layer has undergone displacement S2. So, how much is their relative displacement? It will be S1 minus S2. Okay. And how much is the distance between the two layers? Y1 minus Y2, this one. Then how much will be the shear strain? S1 minus S2 divided by Y1 minus Y2, which is again theta itself, tan theta itself, which is same as theta. Okay. So what I wanted to show you is that it doesn't matter which two layers you take, the shear strain that you calculate will always be the same. Okay. In an ideal case, actually. In a real case, see, who is to say that it will definitely deform like this? It may even deform like this. Who knows? Okay. But in your syllabus, you don't have such complicated cases. You only have these cases where the border or the edge remains straight. So what you can do is, if you want to calculate shear strain, the deformation that is produced, you take any two layers of the object whose displacements you know. Okay. And then their relative displacement divided by the distance between them will give you the shear strain. Okay. So simply written, it is expressed this way: delta x divided by y, or directly theta. That is the general formula for shear strain. Delta x is the relative displacement between two layers. Y is the separation between the layers. Okay. Now, between every kind of stress and the kind of strain produced, there will be a proportionality constant. You know, stress is proportional to strain, or strain is proportional to stress. So tangential stress divided by tangential strain, this ratio is denoted by the symbol G. It's called the shear modulus of the object. Shear modulus, or it's also called the rigidity modulus. For longitudinal stress, longitudinal strain, the ratio was Young's modulus. Tangential stress, tangential strain, the ratio is shear modulus, denoted by the symbol G. Therefore, force parallel to the area of cross section divided by area divided by relative displacement between the layers divided by the separation between the layers is equal to G. This is the formula you will use to solve problems based on tangential stress or strain. Okay. And here they won't trouble you much by giving you non-uniform stresses and all. For tangential stress, I mean, based on tangential stress, if they want to ask you a question, they will ask you a direct question itself. So they'll give you a diagram like this and ask you what is the strain produced, or for how much force you will get this much strain. Such problems can be asked. Okay. And just like longitudinal strain, see what was longitudinal strain? Delta L, change in length divided by L naught, natural length. That was longitudinal strain, and it was a dimensionless quantity. Change in length divided by natural length. Here also, you see shear strain, relative displacement between layers. This will be in meters, divided by the separation between the layers will also be in meters. Like both are lengths. As a physical quantity, if you see, both are lengths. So shear strain also is dimensionless. All kinds of strain are dimensionless. All kinds of stress have the same dimensions, Newton per meter square. Same units, Newton per meter square, and the same dimensions. Okay. Next, the third kind of stress and the corresponding strain: bulk stress, or volumetric stress. How do you apply this? Okay. Perpendicular force per unit area of cross section is longitudinal stress. Parallel force per unit area of cross section is tangential stress. Perpendicular over parallel over, then what is this? Or how do you create this? Basically, on a certain volume, okay, or on a certain object, if forces act at all points on its surface perpendicular to the surface, okay, let's assume the same amount of force acts at every point of the surface, obviously in different directions. It should be perpendicular to the surface. So at different points, the force will be in different directions. That's fine. But let's say the strength of the force is the same there, same everywhere. Okay. Then this kind of stress is what you call as volumetric stress. And how do you calculate it? Bulk stress is again perpendicular force per unit area only. The formula appears similar to longitudinal stress formula. But this area is not cross-sectional area, it is surface area of the object. Okay. As a result of this kind of stress, what happens to the object? You can predict what happens. If the stress is like this, it is going to shrink. Its volume will decrease. Not a particular dimension, all dimensions will change. Okay. And let's say it shrinks to this new volume. That is why it is called volumetric stress. And the corresponding strain it produces is called volumetric strain or bulk strain. And how is it calculated? Change in volume divided by natural volume. What is natural volume? When there's no stress, whatever volume the object would assume, okay, that is called natural volume. So change in volume to natural volume is called volumetric strain. And the proportionality constant between these two, for bulk stress and bulk strain, the proportionality constant is called bulk modulus, denoted by the symbol beta. Bulk stress divided by bulk strain. How is bulk stress calculated? Perpendicular force acting per unit area, but this is surface area. Okay, I'm reminding you again. And perpendicular force acting per unit surface area is what you call pressure. Divided by, how is bulk strain calculated? Change in volume divided by natural volume. Okay. Therefore, bulk modulus can be expressed as pressure divided by, P stands for pressure, okay, divided by delta V by V, where V is natural volume. All right, okay, let me write V naught itself. But see, it so happens that all the objects that we see around us are already under some kind of pressure. You are under some kind of pressure. The pen you are holding is under some kind of pressure. The computer or mobile phone that you are looking at is under some kind of pressure. All the objects that we use and see are under some pressure already. That is atmospheric pressure. Okay, the air molecules, fine. All objects that we see around us are surrounded by air. Air molecules are not at rest. They'll keep moving around, and when molecules keep moving around, they'll keep hitting the surfaces. Okay, and when molecules hit surfaces, they exert pressure on them. So every object that we see is already under some pressure. Okay, you consider a sponge ball. That sponge ball is already under atmospheric pressure. If you apply additional pressure, you can deform it. Okay, whether it's a small sponge ball or a plastic water bottle or whatever it is. Fine, you can compress a water bottle. Now that water bottle is already under atmospheric pressure. You exert additional pressure, you will be able to compress it further. Okay, so for bulk modulus, we don't use this formula. We don't directly say pressure by relative change in volume. A better formula would be, okay, or let me write it this way. To deform an object which is already under some pressure, we need to apply additional pressure. Or decrease the pressure that is actually already acting on it. Okay, so effectively what I'm trying to say is that a change in pressure is needed to deform an object. Because it's already under some pressure, you change the pressure, you will get deformation. You increase pressure, it will get compressed. You reduce pressure, it will expand. Okay. Therefore, bulk modulus is expressed as change in pressure divided by delta V by V. And there's one more point to keep in mind. If you increase the pressure on an object from outside, it is going to shrink. It is going to get compressed. So we know that if delta P is positive, increasing pressure means delta P is positive, delta V will be negative, volume decreases. Okay, and reverse. If you decrease the pressure, volume increases. Change in volume will be positive. So delta P and delta V will always have opposite signs. Now, if they always have opposite signs, that will make bulk modulus a negative value. But just to keep it a positive value, we include a minus sign also in this formula to ensure that bulk modulus will be positive. Okay, we want to keep the modulus of elasticity positive. Therefore, the formula relating bulk modulus, volumetric stress and volumetric strain is this: minus delta P divided by delta V by V. Okay, questions based on this are very common. And see what you have here: delta V by V, change in volume divided by natural volume. This is called relative change. Of course, in longitudinal stress also we had delta L by natural length. That's called relative change in length. Here it's called relative change in volume. And relative change multiplied with 100 makes it percentage change. Now, if any of you remember, we had discussed relative errors and percentage errors in the first chapter, units and measurement. For small errors, we calculate in one method. For large errors, we calculate in another method. Okay. So questions similar to those can be asked here. They may give you a change in pressure and ask you what is the relative change in volume, what is the percentage change in volume. And if you know percentage change in volume, you can tell change in dimensions. For example, suppose it's a sphere. For a sphere, you know volume is 4 by 3 pi r cube. So if you know what is the change in volume, you should be able to tell what is the change in radius. If the changes are small, you will do it one way. If the changes are significant, you will do it in another way. So I want you all to revise those things before the next class. Next class will be tomorrow itself. We are going to finish this chapter tomorrow. So I just want you to revise how to calculate relative and percentage changes. Okay. In that chapter, we talked in terms of errors. You revise that itself. How to calculate relative and percentage changes in one quantity depending on relative and percentage changes in another quantity. Okay. Briefly revise this, then you'll easily be able to apply this formula to solve problems. Okay. Fine. We'll continue in tomorrow's class. Tomorrow's class will be from 7:30 to 8:30. 1 hour class. Okay. So what all did we discuss today? Some more questions based on longitudinal stress, breaking stress in particular. Okay. Then we talked about tangential stress, tangential strain, then volumetric stress, volumetric strain. So tomorrow we'll solve problems based on all this and close this chapter. Okay. Thank you all. We'll continue tomorrow.